Hi, I'm Peter Glover, and I'll be going through the physical science sample papers with you through a couple of DVDs. The first DVD is going to be paper 1, which is physics, and the second will obviously be paper 2, the chemistry. Now, I must stress that these are sample papers. I set them, and I'm not a national examiner. So if they aren't exactly the same as the past papers or as the paper that you're about to write at the end of the year, don't worry too much. The point is that these are the kinds of questions that you're going to get, and it's just a little bit of extra practice because, as we know, practice makes perfect. Now, this is called the exam walkthrough. Funnily enough, we've got less time to do the walkthrough than you have to write the exam. So I guess it's going to be more of a run-through. But don't worry, what I'll try and do is highlight the most important points and the really key things that you have to learn. You've always got the website that you can go to, learn.co.za, and from that website you will be able to pull down the paper and the marking memorandum. Having said that though, don't go looking at the marking memorandum until you've had a good crack at doing the question yourself. All right, let's start. We're going straight into section A, and we're going to look at these short questions, which are sometimes called one-word answers, but of course they are usually one term because sometimes you get 2 words in it. Let's take a look. Right, the first of the one word, one term. The minimum amount of energy required to remove an electron from a metal surface. Now, we know that this can be done with light, as in the photoelectric effect. In fact, it can also be done with heat. But the point is that that minimum amount of energy has the same name for both processes, and it is the work function. In other words, how much work do you have to do to get rid of the electron from the surface? The energy of a body due to its state of motion, okay, that movement energy, we all know about that, it's kinetic. The bending of light when it enters an optically more dense medium, all right, it will also bend when it enters an optically less dense medium, but the fact is that either way, it is a bending known as the refraction of light. The product of the magnetic field strength inside a coil of a conductor, okay, magnetic field strength, and the area enclosed by that coil, it's this thing phi, and it's the magnetic flux. Good, got that, and of course that's in the data sheet, isn't it? Increases the capacitance of a capacitor when placed between the parallel plates of the capacitor. And that is something which is known as a dielectric. So if you put something in between the plates of a capacitor, you increase the capacitance. In other words, you increase the capacity to hold charge on those parallel plates. Right, second question is on correcting false statements. Now, just be a little bit careful, and I'm sure you'll be aware of it now, but up until last year, this was a case of first deciding whether the statement was false or true, and if it was false, you then had to correct it. Now, just to avoid all confusion, because I guess people were correcting true statements, but all of the statements are false, and you have to find out what makes it false and correct it in order to get your marks. So let's have a look at question 2. When you hold a 1 kilogram mass in your hand with your palm facing upwards, the reaction to the weight of the 1 kilogram mass is the normal force of the hand on the 1 kilogram mass. Now the problem here is to do with these things called action-reaction pairs. There are 5 things that you need to remember for action-reaction pairs. This is all to do with Newton's third law. The first is the pair of forces are equal in size, or is equal in size, I'm not sure. They are equal in size, the forces. Secondly, they act in opposite directions. Thirdly, they act simultaneously. So let's imagine that because there's an action, we wait a while, and then there's a reaction. The reaction force is simultaneous. And I always try and explain it this way. You can't touch without being touched. So the moment my one finger touches the other, my other finger touches the one. So they are simultaneous. The next thing is they are the same kinds of force. Okay? They are the same kinds of force. Now, this is the one that gives us the clue for this question. We're saying, here is the normal reaction of my hand on the weight. The weight is a gravitational force because the Earth is attracting that 1 kilogram mass. But remember that the 1 kilogram mass is also attracting the Earth. And therefore your action-reaction pair here is the gravitational pull by the Earth on the weight and the weight's pull on the Earth. It may not be very much, but it's there nonetheless. So it is incorrect to say that the action-reaction pair is the normal force of reaction by my palm on the 1 kilogram mass and the weight of the mass. The other thing is that the two forces in an action-reaction pair act on different bodies. Don't forget that. So if you can find two forces that meet all of those requirements, the chances are quite good that you've got an action-reaction pair. All right, let's take a look now at the second question. 2.2, the refraction and diffraction of light both involve light bending when it passes into an optically denser medium. Well, that is incorrect because diffraction is about if you like, a bending of the light or bending around an obstacle, around a barrier, through a narrow gap. It doesn't involve an optically denser medium. It doesn't involve what happens with refraction, which is light bending when it goes from air into water or from air into glass. Diffraction is about bending at an edge or in a gap. All right, if two resistors of 3 and 5 ohms respectively are connected in parallel in a closed circuit, in other words, there is charge flowing in it, the potential difference across the 3 ohm resistor will be higher than the potential difference across the 5 ohm resistor. Now that is nonsense for a very good reason. If we take a look here at two resistors in parallel, and that would be a 3 ohms, remember, I'm just being lazy, and that is the 5. The point here is that the potential difference across those two resistors is exactly the same. And because it's the same, that means that your current in the two resistors will be different, because current times, this would be I3 times 3, and this would be I5 times 5, and the current through the 5 ohm times 5 ohms must be equal to the current through the 3 ohm times 3, and therefore the currents must be different because the potential difference across both of them is the same. So this is incorrect to say that they'll be higher. They must be the same, and you put that into your own words.
Learning Channel offers an extensive educational collection ranging from grades 8 to 12 in alignment with the National Curriculum Statement. We offer DVD and workbook sets in a number of different subjects. To buy the Learning Channel series, check out our website on www.learn.co.za or call us on 011 639 0179.